Hello everyone. Welcome to the CATIA Systems Masterclass. Today we will talk about automated tests in Modelica with Dymola and the testing library. My guest today is Marco Kessler. Marco has just returned from the Modelica conference where he delivered the tutorial on that topic. Today he will show the testing library's capabilities and show how to use it. He will create and run tests in Dymola first manually, then automated via PowerShell. After the session, Marco will spend some time to answer your questions. You can write them in the Q&A section. I wish all of you good learning, and Marco, the stage is yours.
Okay, hello everybody, and welcome to this CATIA masterclass about automated tests in Modelica with Dymola and the testing library. So thank you, Gitana, for the introduction. As you said, my name is Marco Kessler, and I work since about 12 years with Dymola and Modelica. My job here at the SOS Systems is to implement Modelica models for the various commercial libraries we provide and to provide test cases and test infrastructure. And today I want to show you how we build test models for our Modelica classes and how you can apply that on your own classes. Let's have a quick look about the content of today. First, we'll talk a little bit about the motivation we need to build test cases. So what's the reason why we want to do that? Next thing is the testing library. We will have a look at the basic working principles of this library. Then we will switch to the demo section and build multiple test cases together. After that, we will automate the test execution. And finally, we will summarize everything in the takeaway section. And after that, you'll have time for questions. So what's the target audience of this masterclass? It's basically everybody who is doing simulations with Dymola. It could be someone developing a library, could be someone developing a few blocks, or someone who is using examples from another person. Because all of the time when you do simulations, you will make some modifications here and there. It could be just some parameters, or it could be changes to the model at all. So whenever you change something, you will influence the result you obtain. And we want to make sure that the results you get are the same on another machine or the same on your machine in the future when something changes. So therefore, this masterclass is basically for everyone working with Dymola. The main target is people which never worked with the testing library before. So we'll show some fundamentals of the library. But there are also informations included for people who are already working with the testing library. For example, the PowerShell module, which we will present, and the clock tests, which are both recent additions to the library. So, motivation. Why should we invest into continuous testing? One of the most important aspects is you want to detect errors early. If something goes wrong, so if you had a model which worked and it breaks, you want to detect this error on your machine and not let your users find the issue. So, tests will help you to deliver high quality products to your customers. Next thing is, if there is an update to your infrastructure, to Dymola, to the libraries you're using, you have to make sure that your models still work. And if you have good test cases, you can update without worries because you just run your test cases and then you will detect the small issues quite easily. And at the end, the main idea of testing is we invest some time now to save a lot of time later because updates and errors which you didn't expect will hit you more often than you want. So when we do a simulation with a Modelica model, we have several dependencies. One of the dependencies is the tool we are using, in our case Dymola. If you run simulations in Dymola, you have a lot of settings you can do. You can change the solver, you can configure the solver, and you can make a lot of settings in the advanced with the advanced flag. So you can influence how the model is generated, the code you get. So there are a lot of things you can set up, and this might influence the simulation results. So one dependency is the tool we have and the settings we choose. There's another dependency which is maybe not that important anymore, the Modelica language itself. It's not that important anymore because it got quite stable. That was not always the case. There have been big changes from Modelica 2 to 3. And so when a new language version comes out, you also want to make sure that it works. Something that's more important or more frequent to change are the libraries you use. Most models use the Modelica standard library, and often you might use other libraries as well. And if those libraries get updates, you again have to test somehow if everything still works as it should. And for all these dependencies and for all those cases we talked about previously, we introduced a testing library. The testing library is shipped with Dymola. So if you have Dymola installed on your computer, you just have to load it and you can go ahead and start testing because it requires no extra license. It was designed to allow quick and easy testing. So you just build your test cases like regular Modelica models. You don't have to learn much new. And so you can be quite fast in building test cases. Because we test everything in the natural environment of a Modelica model, which is just a tool, in our case Dymola, you get some extras on top, like if you do refactoring, if you change class names, if you change variable names, those changes are automatically applied by Dymola on your test cases. This is not the case if you use an external tool to run your test cases. Then you might have to update your configurations. But because we do everything inside Dymola, we get that for free. And finally, the library was designed to give users full control. Users can decide which are the important signals, which methods do we want to test, and what are the allowed tolerances. Okay, let's go now into the testing library and have a quick look. Here we see some of the most important packages we have. So we have a package for continuous checks, one for clock checks. Let's see what the difference is. In the continuous checks package, we have blocks for different data types, for booleans, integers, reals, which allow you to perform comparisons. And the comparison works like this. You have two connectors usually, one for the actual signal, which is the one which is produced in the current simulation, and one for the reference signal. The reference could come from anywhere. It's just a typical Modelica connector, so you could connect another model to this one, you can connect a reference result, something read from an external file, or whatever. And what the block now does, during simulation, it compares both input signals. And if they match, the test passes. If it doesn't match, the test fails. For the continuous package, this happens continuously during the simulation, which means the comparison is performed for every solver step. With the clocked package, we have now new blocks which allow you to define at which point, at which interval you want to perform the comparison. This has several advantages when we deal with recorders, and we will see that later, what the reason is for that. So we have similar comparison blocks in this package, again, for all the data types. For increasing dimensions, you can compare scalar signals, 1D, 2D, 3D, but with the clocked package, you define the tick rate and at which interval we want to perform the comparison. Then there's the runners package. In the runners package, we have multiple functions which you can use to build your test cases, to run them, or to create reference results. Okay. So let's look at the typical Modelica example. In this case, we took it from the new Sustainable Supply Systems library, which will be shipped with the next Dymola release. Here, we compute costs and energy consumption for various components in a smart energy home system. When we simulate this model, we go through multiple stages. The first stage is the check. Here, Dymola will check if you have enough equations for the amount of unknowns you have. Next thing is the model is translated. So your equations are causalized and you will end up with an executable which you can use for simulation. If anything goes wrong in those first three stages, you will notice Dymola will give you an error message and say check did not pass, translation did not work, or simulation was aborted. And you will not end up with a result. So in those cases, we usually don't need extra test cases, because we can use our typical examples we have in the libraries. But when you get a simulation result, the question is now, how can you be sure that the result is correct? And how can you be sure if the result was correct once, that it's even correct on the next day when you made an update? That's where the testing library tries to help you. So now let's look how we can build test models. Here we see a very simple Modelica example built with components from the Modelica standard library. At the top, we have just some components building a mass spring damper system using parts from the Modelica standard library. To transform this example to a test case, all we have to do is add some sensors, identify the signals which are important, and then use comparison blocks from the testing library to compare the actual signal against the reference, or to check if our signal is within a given range. In this case, we check if the force acting on the wall is in a given range. For example, it should be positive, so that's quite an easy test to do. And in this case here, we check if the speed matches a reference we are reading from somewhere. After you build the test, you can execute it just by simulating your model. You get then multiple ways to check if your test passed. One way to do that is to just look at the visual representation. In the diagram layer, you will see immediately if the test passed by looking at the colors. So the test here on the right hand side passed because the bar at the bottom is solid blue. The bar is split into two parts. On the left hand side, we see what the expected result is. On the right hand side, the actual result. So you could also write negative tests and test something which you expect to fail. So if the colors match, the test is passing. In this case, we see here colors don't match, this test failed. And here we have a visualizer which summarizes all the tests we have instantiated and gives you a quick overview of what's happening. So that's the visual representation. There is more. We also get information in the simulation log. So when the simulation is terminated, so that's the final solver step which is taken, that's just before the simulation is finished. Every block is writing its final result to this terminal section. So you can just have a look at the terminal section and scan the first column for the result, and you see the test name and the result. And at the time instance where a test fails, you get a warning printed to the simulation log with some details about the failure. With default settings, you don't get too many details, but you can increase the verbosity of this one. Okay, let's now switch to Dymola and have a look at the testing library, how it looks live. So now I've started a new Dymola instance. And we don't see the testing library yet. So what we have to do is we go to the File menu, Libraries, and load it from there. Here the testing library is listed, click on it, it's loaded. So here are now the important packages I mentioned before, the continuous checks block, continuous checks package for the continuous checks. You can open it, here are the comparison blocks. Then we have the clocked package for the clocked comparisons, and we have the runners down here. There's another package which is good to know or good to look at, which is the user's guide, because we have here some detailed information on certain topics, like how to run your test models, how to set up tolerances, and there is also a detailed tutorial which gives you step-by-step instructions how to build test cases and run them. Okay, let's have a look now how you can create test models. So if you go to the runners package, you have some functions available here, but you don't have to go here because we also have the toolbar. After loading the testing library, you can go to the tools ribbon and open or call some of the important functions from the testing library from here. So that's the testing toolbar. Here you can run tests, or you can also create new test models. Let's start with a test package. So I just call this function here. I could enter a name. I used the default name. So I get now an empty test package. When you have activated this test package in the package browser just by using double click, you can add now a test case. We go again to the toolbar, say create test case. Now we have to enter a name. You have to preserve the test underscore part at the front because that's how tests are later identified. So you just enter here the name of your model, my model. In future versions, it will not be necessary anymore to enter this by hand. It will just be, the prefix will be added automatically for you. But at the moment in this release, we have to make sure that this test underscore is preserved. So that's our test case now. And here we have an empty, almost empty test model. What is already instantiated for you are the dashboards, which give you a summary of the test cases. You can keep them or just delete them, they're not needed. But if you want them, just keep one of them. And you have the global test setup block. Here you can do some global settings. Two of the important things you configure here are the mode you're running in. So we can say that we are running in check mode, which means tests are performed, or create references, which is when we are recording results. And you can turn everything off by using skip checks here. And that's also the place where you can increase the verbosity or decrease the verbosity of the error message you see in the simulation log. This block was more important in the past when we used continuous references for our recordings. So that's where you configure the file path for your continuous reference files. But that's not something I recommend anymore. Nowadays, we use the clocked references. To create a test model with clocked references, you again use the toolbar. So I activate my test package, go to the toolbar and create a new clocked test case from here. Enter the name. I keep the default now. And what happens now, it's quite similar to the one before, but now I also get a clock setup block. This clock setup block defines a clock tick rate to perform the comparisons. So if I open it, I can here configure that I want to have tests every 10 milliseconds, for example. And it also defines the CSV file where we store our results to. You can have multiple clock setups, and we will see later how to use them. With each clock setup, you configure the time. So if you have multiple clock setups, you will usually use multiple or different clock times and different CSV files. Okay. So much for the first introduction for the library. Let's now see how we can create test cases. What we do now is we want to test against known values, which means we have a block with known input and we have an expected output. So that's one kind of test case we can create. And we do that for this ideal drive model. This model is taken from the Dymola models library. That's another library you get free on top when you buy Dymola. When you just have to load it like the testing library from the libraries menu. And it's some kind of foundation library for the other commercial libraries we have. It contains many simple models which are easy to parameterize and are stable and give you quick results. So this drive model is not modeled in a very deep physical detail. So if you look inside, you don't have electric components. It's just modeled to act like a drive from outside. So you have this connector here where you request a torque, and this torque could be limited. And then you will get a torque at the flange, and the required power which is needed to drive the flange is drawn from the electric side. That's what this model does. And to make it a bit more realistic, we have a limiter included, which tries to act like the figures we see here, or like the curves we see here. So if you have a drive, you have usually two limits. You have the torque limit and you have the power limit. In the lower speed areas, the torque limit is relevant. So on the x-axis, we see the speed. When you increase the speed, we cannot request more torque than this maximum torque value gives us. But at one point, we reach the power limit, because when we increase the speed, power will also increase linearly due to the constant torque value. When we have this point, to get a higher speed value, due to the power limit, we have to reduce the torque. And now we have a block which tries to implement this behavior. Let's have a look how it works and how we can test it. Okay, what I did is I prepared almost finished test library, and we will add the remaining parts. So we have this test library here prepared, and here this limiter is already instantiated in a test model. But the checks are missing at the moment. So let's first now simulate the model to get a bit more an understanding what the block does. Switch to the simulation tab and make some space here. Okay, we have here the torque limiter, and this one should act like we saw previously or before on the slide. What it does is we have here the desired torque, and we get here the allowed torque, the set torque value. So if we compare the desired torque 60 with the set torque, we see it's not limiting at the moment, because you have three parameters. You can enable torque limitation, and if it's enabled, you can define the maximum power, in this case 1 kilowatt, and the torque limit, in this case 50 Newton meter. So let's enable the torque limitation and simulate again. Now we see the requested torque is 60, but that's the torque we get. As we're ramping up the speed, so this input is the current speed we will have, the torque is reduced after half a second, because after half a second we have 20 radians per second. 20 times the 50 gives us the 1 kilowatt we have maximum available. So after half a second, this torque value here is reduced. So we see how the block is operating. Now let's create a test for this block. We will start with a very simple test first. What we do is we check if this parameter is working, enable torque limitation. So what we do is we just go to the testing library, to the checks package, and from there choose the compare real block. This block, because it's not in the clocked package but just in this top level checks package, performs a continuous comparison, which means we need a continuous signal to perform our check. As a reference, we can just use the torque value, because no matter what we request, we will always get it, because the torque limitation is turned off. And so this is now our ideal torque value we can use as a reference, and we just compare it with the output value. So very simple test case, but it allows you to test if your parameter works as it should. After setting everything up, you simulate it, and as we expect, the test passes. I recommend to give this block a better name, because the name you have for the block is also printed here. So if you call this one check limit off, we also see this name when we simulate here in the simulation tab. Okay, that was a simple test case. Let's add now one that's a little bit more complex. We turn the torque limitation on. And now let's think a little bit how we can test this. Let's go back to the picture. So what we want to test is this blue curve. How could we test it? I mean, if we want to provide a reference signal, we will probably end up with the same equation like we're using in the block inside. We will be dividing the power by the current speed. And it makes no sense to check against the same equation which we're using in the block. So in this case, we have another signal which is easy to use and which is not exactly the same. We will check on the power. We can, if you look at the power, you see that it's acting like a step signal, like a ramp signal. So it's first increasing linearly, and then it's reaching the maximum value. So it's just a ramp. So let's use this to check against. So what we do is now we just duplicate the ramp we have. We give it a better name, pref. We say maximum value we have is 1000, and we already saw we will reach the limit after half a second. So that's our reference signal. Connect that. And now we have to compute the current power we have. I just duplicate this block here to get faster to the block I need, because in the math package there is this product block. Use this one, which did not work. Let's try it again. Math package product block. Change. Yes, now it worked. Okay, give this a better name. That's the current power we have. And to compute the current power, we just have to multiply the speed we have with the current power, with the current torque we have. And now we connect that to our check block and simulate. And the test passes. So again, give this one a better name, check limit on. And now let's look a little bit into details of what's happening. It's always good to check what you're actually comparing in your model. To do that, you can just go to the simulation tab and erase what you have here, and just click on this check block, maybe also delete this one, and then you get the, let me simulate again. I renamed, that's why it didn't work. Okay, I renamed, so now it works. I have now my check limit on block, and now I can compare several signals. I can look at the actual signal, at the reference signal, and I can look what the result is. So somewhere here is the test result. Yes, here. You see the test passed. Test is okay. And you can also see if you were always inside tolerance. Because these are very important signals which you might plot often, there's a more convenient way to do that. Let's first break our test. What we do is we just alter the speed signal, but don't update our reference. So this test will fail now. And what we can do is we can go to the toolbar and select this one, run and plot all. So it will run our test model and create a plot for all check blocks we have. Did I select the wrong one? So, sorry, I think I selected this one, plot failures. Plot failures just plots the one which don't work, and plot all should plot all. Yes, now we have two plots. Okay, because we have two check blocks, we get two plots now. And we can just maximize it, and then we see the reference signal and the actual signal. And we also see the area we are inside tolerance and the test result. So that's a very quick way to just create a plot for all your checks you have. And you can maximize them. Just click on the Windows button here and step through all of them. So that's something I recommend you do. Okay, that's now our first test case. Let's continue. We want to build this drive model. And inside this drive model, we have this torque limiter. So the torque limiter is tested. We can assume that it works as it should. Let me save this one first and then, okay, go back to this drive. So what I did, I created a setup where we are ready to simulate. So we request a certain torque from the drive, and we can have a look inside the model. Here, the torque requests can be limited by the block we saw before. Then it can be filtered. This first order element is used to mimic the electric time constant of the machine. It's optional, you can also disable it. And then the torque, which is obtained here, is just applied with this torque source to the rotor inertia, and the remaining torque is available at the flange. And the power you need is drawn from the electric side, multiplied with an optional efficiency. So that's how this block, how this model works. Let's first simulate it and see what happens. Okay, let me prepare some plot windows. So let's just look at the speed we have. So that's the speed we get at the flange. So the machine is accelerated, and at one point the speed reaches its maximum value because we have this load torque which is increasing with the speed. And when we look at the torque, it looks like this. So that's the torque we have available at the flange. It looks a little bit strange at first, but it makes sense. If you look inside the component, we need some of the torque to accelerate this rotor inertia. And the torque we have internally available is the one at the flange A of rotor inertia. So that's the torque we get here after torque limitation. Then we need some of the torque to accelerate this inertia, and the rest is available at the flange. So when you create now a test model, you have to decide which are the important signals. I could use the internal torque value, which would result in a test case which neglects what I connected from the outside. So it might not be important for me what I connected from the outside. It could be just important to let the model run. So if I don't want to test the outside components, I would use these variables. But if I want to check the overall model, the overall example, I would use the torque value we have outside. So it's your decision which to use, or you could use both if you want. So in this case, we will just use the values here. And now let's see how we can test against that. So the problem is now, let me go back to the plot. If we look at this blue torque line, it's quite hard to provide a reference like this from a typical source block. So what we usually do is we simulate our models, then we look very carefully if everything behaves as it should, and at one point you will decide, okay, this is fine. This is now my reference result, and I will test all my future simulations against this reference. To do so, we will use recorders. So I already prepared this test model, which can work with clocked recorders. So we have here the clock setup. What's missing are the recorders. So we go to the testing library, not the top level recorders package, these are the ones we don't recommend anymore, but the new edition, which is the clocked recorder. And then you choose the clocked recorder matching your data type. So in this case, we have a real signal, so we need this real recorder. And what we do next is we give this a good name. So check speed, for example. Okay, so when we connect now this signal here to the speed value, what happens is, because this block here is clocked, Dymola will clock your whole model. That's not what we want. So we have to add a sampler. You can use the samplers from the Modelica standard library for that. So if you go to Modelica, there's this clocked package, and there you find a lot of blocks which are working with clocked signals. But because we need the sampler often, we have created a link here. So if you go to testing, clocked links, where we have links for some important components. So in this case, we need this sampler block. And when we attach it here, this is where we break everything up so that this part runs continuously and only this part here is clocked. Next, what we have to do is we have to configure the clock. So we set the clock already up here and we configured the file name already, but this block does not yet know with which clock it should run. So we have to open the parameter window and change the configuration here. So we just click on the pull down and say we use clock setup 0. Then we duplicate everything to have a second check. Give this one a good name because we want to check the torque as well. And connect this one to the measured torque. Okay, so next thing we do is we create a recording. To do that, you could open the setup block and switch the mode from check to create references. But because this is quite annoying to do all the time and often you forget to change back, we have a function which does that for you. So you go to the toolbar and you choose either create references or update references. If you use create references, this dialog pops up which asks you if you want to overwrite existing files, and you could change the solver setup if you want. But when you're sure that you configured your file name correct, you can just use update references, which will not show a dialog, just run the simulation and create the file for you. So let's look now at on our hard disk. Inside our library, we configured that we want to have the CSV file in the resources folder. So if you look there, that's where our resources folder, where our CSV file was created. We can open it, and then we see that we have 3 signals recorded. In the first column, it's the time. The time is always recorded, unless you deactivate that. And in the other columns, there's the speed and the torque recorded. The name which is used is just the block name. So you can change the trajectory name here if you want. If you don't change it, the name of the block is used. And if you don't want to record the time, you can turn it off here. But usually you want to have that in the file. So with this CSV file now, the next thing you would do is you commit it to your Git repository and then use it as a reference in future simulations. So to do that, to compare against that reference, all we have to do is simulate our model again. And then we see if the test passes. So we see both tests passed and we have 401 clock ticks. Let's have a look now how this behaves. So again, go to the testing toolbar and select run and plot all. So we should end up with 2 plots now. Yes, we have 2 plots. And if you zoom in here a little bit, we see all the dots. The dots are when the clock was ticking. And if we zoom here, especially in this range in a little bit, we hopefully notice when we compare it with the original signal that our clock is not ticking fast enough in this area. So here we would need a higher clock tick rate to capture at least 1 point of this transient curve here. And for the later parts, our clock is fast enough. So what you can do, you could increase the whole clock tick rate for the simulation, but it's not, in this case, doesn't make too much sense. Instead, we can vary the clock rate through the simulation. For that, we will use from the links package this sampled segments block and an event clock. Change the clock setup to not use the parameters here, but the connector, so external setup. And then with this event clock, again taken from the Modelica standard library, we can create our events as we want to let the clock tick. And this sampled segments block is easy to parameterize. You just open the table window and then it's comparable to parameterize like tables you might know from the Modelica standard library. So we say from time 0 on, we want to have a data point every millisecond, and after 0.6 seconds, it's enough to have a data point every half second. So let's now update our references and check if the new clock rate is good for this example. And again, run and plot all to compare against our recording and get nice plots. So let's zoom in now a little bit. We have here still enough data points available. And here at the beginning, the clock is ticking a lot faster. We have a tick every millisecond, so it's more than enough here for this step. So you could reduce it you could also reduce it here a little bit, but that was just to show how you can vary the clock tick rate during the simulation and act on the dynamic phases you have. Okay, so this was now the showcase to demonstrate how you can make recordings. There is another thing you can do quite similar. In this case, we have a finished test model, but I want to show you how you can use these recordings to test existing examples you have. So in this case, we just instantiated an example from the Dymola models library. If you look inside, this is a battery which is charged and discharged. So I just instantiated the whole example, and to create a test case for it, I just made a new test model, instantiated it, and accessed the important signals here with these real expression blocks. Again, I have to sample, and I have to use the recorders to store everything in a CSV file. The rest is already prepared. The CSV path is set up here, so I can just click Update References, and then we will get our recording. So let's check. Here again, yes, now we have our second recording, the battery recording. We can look into it, we see we have the SOC recorded and we have the voltage recorded together with the time. Okay, let's now simulate this one again. So what happens now, surprisingly, are two things. First, here it looks like the test passed, but you see here that the clock was just ticking once, and you see here that the test failed. The clock was ticking 601 times. Why is this one not up to date? That's a little bit of a pity at the moment. What you have to do is, if you go to the animation, to the simulation view, for this visualization we are using the animation features of Dymola, and sometimes you have to make sure that the time slider is at the end. So the actual result, the one you can really trust, is the one here. So that was the first thing which was strange. Second thing is, why are the tests failing? Let's have a look here. Let's have a look how big the error is, and then we see the major deviation, the major delta we had during the simulation. So the biggest deviation we had is very tiny in both cases. And in both cases, if you look at the translation log, we see that we are checking state variables, because the SOC is a state variable and the capacitor voltage in the battery is also a state variable, and the capacitor voltage directly influences the voltage we have at the terminal. So we're checking state variables, and state variables can change within the solver tolerance when you do simulations. So we did not set the tolerance, and what we have to do is now either use the very small deviations we saw before as tolerance, as absolute tolerance, or we just use around the typical solver tolerance. I usually recommend double the value, and then you'll save also for future changes. So simulate again. This one did not work. Now the test should pass. Okay, yeah, this test passed. So this is now our third test case we have. Okay, let's summarize everything. What did we do now? We tested against recordings, which means we have a recording we made, and we have a reference signal and we have an actual signal, and there might be very small deviations. To configure that, to configure the allowed deviation, you have the absolute tolerance parameter and the relative tolerance parameters. So when you make the recording, there's something happening. And now I want to explain to you why I don't recommend the continuous recorders anymore. So what happens if you have your reference trajectory and you make a recording, you store a limited amount of data points to a file. So even though the variable is continuous during simulation, you cannot store everything to the hard disk. So you have some kind of output interval configured in Dymola. And when you store everything to a file, you don't have all information available anymore. So previously we used the combi timetables, which uses MAT files and text files, and the STF library. And when you use those libraries or the table blocks from those libraries to play anything back, then you will need interpolation, because when we compare the values in the simulation, we are continuous again. So we have to interpolate between the known points. And if you compare the original trajectory to the one which are now which we reconstructed now from the recorded data points with interpolation, you will very soon be outside the tolerance. So in this case, we use a simple linear interpolation, and you see you would have to increase the tolerance very big, or you would have to store a lot more data points to be inside the allowed tolerance band. You could also change the interpolation to spline interpolation, but this will not work if you have somewhere a step in your signal, if you have an event where your signal jumps. So you're some kind of limited. Therefore, we implemented this new table block, which allows to store values to a CSV file, and the value must be clocked. That's the whole idea behind that. So we have this clock ticking, and whenever the clock ticks, we store a value. And the benefit is now, when we compare against this recording, we will just check when we have those known values. So when the clock is not ticking, we are not comparing. Therefore, we have no issues with interpolation. Okay, so much for test creation. Let us now continue with automated test execution. There are two things we can do there. We can automate test execution inside Dymola, and we can do it on the command line with PowerShell. Let's first do it in Dymola. It's quite simple. You just activate your test package, make sure that it's active, go Tools, Testing, and select the runner via Run Tests. Then you hit OK. You could do some configurations, or you just hit OK. Then it will detect all your test cases and run them. So what we see now in the command line is that 3 test classes were identified, and they are now executed one by one. Then you get the final summary. So that's what you can do in Dymola. It's not, the output is not very pretty, to be honest, but it works, and you can use this function in your own functions and in your scripts. Okay, but we have something better now. We implemented the PowerShell module. This PowerShell module is called PS testing. The entry point is, for example, here in the testing library. You can go to the user's guide and open this continuous integration page. And here we have 2 links to functions which allow you to open the folder where everything is stored. So let me show you the documentation first. So I'm now here in the Dymola installation directory, in the testing folder, resources directory. That's where PS testing is, how PS testing is delivered to you. And here you have a very extensive HTML documentation, which tells you hopefully everything you need to know about this PowerShell module. First, we will start with installation of PowerShell on Windows and Linux. Then we will continue installation with the module, and then how to use it. Then you'll have a lot of pages telling you how to create test scripts, and finally how to do everything on GitLab. So I won't show that now in detail, but we will do some live demos. So what we did on this machine, the PowerShell module is already installed. So what we can do is type here get module PS testing list available. And now we see, okay, PS testing is installed in this version, and these are the commands it provides. The most important one is this one, invoke testing. With invoke testing, we can perform our tests. So the first argument we have to set for invoke testing, we can discover that by just hitting space, then control space. We can check, the first argument is the test type we want to perform. We can check a library, we can simulate all examples in a package, or we could run the unit tests we created with the testing library. So let's perform unit tests. The next argument, we can just hit control space. The next argument is the library you want to test. And now you see all libraries which are available on the Modelica path. The library we created before, the test library, is not listed because it's not on the Modelica path yet. So what we have to do is we either have to change the Modelica path permanently with the system environment variable, or we just alter it temporarily with this argument. And I stored the library in documents Dymola. So now I added it to the Modelica path. I can hit control space, and here the test library is visible. So we can select the test library, hit enter, and now the simulation of our test cases is performed. So in the background, sorry, let's ignore this one for now. Okay, let's start again. So we hit enter. Now Dymola is started. It loads all the libraries we need, and it discovers the test cases. And we have 3 test cases, and when there's a failure, it's printed to the terminal. So 2 of our test cases passed, 1 failed. And so that's the basic thing you can do with that PowerShell module. There's a lot more you can do. You have a lot of parameters. So you just hit dash, then control space, then you see all the parameters you have. So you could change the Dymola version, the setup file, or maybe the output. Let's change the output. We can switch to detailed output. So if we run our test again, we'll got more information. We'll now see which Dymola version is used, what's the setup file we use, the internal one, I will talk about this one later, the compiler we used, and a lot more. And we will also get information about the tests which passed. So what you also can do with invoke testing is check a package. So we could just check the complex library, for example, which is delivered with the Modelica standard library. So again, let's use detailed output and see how it works. So Dymola started and we check the package. Or you could simulate some examples. So you could simulate in Modelica.blocks all examples we have. Simulate, sorry, like this. Okay, so we have 28 examples and now they are all just simulated one by one. PID controller, filter, and so on. As this takes a while, I just hit Ctrl+C and now everything is cleaned up. So Dymola is shut down and the temporary working directory which is used is cleaned up. So that's what PS testing can do for you. Okay, again, let me summarize. So we have now this PowerShell module which allows you to perform your tests on the command line. You can run unit tests, you can run checks, you can run simulations, and you have a lot of options you can configure. If there are any questions how to use it, just refer to the extensive HTML documentation which is included. Some thoughts about the PowerShell module. So what we do is we run everything with a default settings file, which means we ignore the setup.mx file in your user folder. You can change that if you want, but this allows us to test everything in a neutral Dymola environment without any changes made by the user to the advanced flags, for example. Next is, as we don't use the default Dymola setup.mx file, we don't know which compiler to use because that's configured in this one. So we just detect the Visual Studio installations and use the latest compiler. If you don't want it, you can change that. We also detect Dymola installations. Default is to use the latest Dymola version, but you can also, again, change the Dymola version. And finally, the goal is to run everything silently in the background without any windows popping up and no leftovers on the hard disk. So with this PowerShell module now, the next step which you can do, which we can't show today as we are running out of time, is you can create test scripts and run them quite easily on a build server like on Jenkins or GitLab. Then you create the JUnit XML and most of those servers understand that. Okay, so now we're coming to an end. Takeaways of today's masterclass. First, I hope I was able to convince you that Dymola provides a full testing solution for Modelica models. With the testing library, you can create and run tests inside Dymola. And with the PowerShell module, PS testing, you can automate test execution on the command line and execute your tests on a build server. Moreover, with the testing library, you can test all kinds of Modelica classes. Here, in this masterclass, we just covered testing blocks and models and examples, but you could also test functions, so everything is possible which you create in Modelica can be tested with the testing library. And we have the continuous tests available and the clock tests, both with their own advantages. And finally, we have shown that the library allows you to specify by your own what the important signals are and what tolerances you would like to use to test. Okay, this is it. We're now at the end of the presentation. There will be a recording available in this CATIA MBSE user community. You can access it with this QR code or with the 3D Swim app. And you can also stay in touch via that community, so we could ask questions there after the session and we can answer them there. But now I give the word back to Gitana and we will continue with the questions now.
Okay, thanks, Marco. It was really incredible. So we had everything live online. And it was awesome to listen and to watch what you performed. You are
Thank
right.
you.
The people will be able to show the replay to replay this session on our community, MBSC Cyber Systems community, as well on the YouTube, and also the LinkedIn also will keep the recording as well. So I think that people asked, yes, they asked about the recording, so the answer is already given. So I have a question for you about the existing project, and what is the best tactics or strategy to introduce this testing into the existing project?
Yeah, if you already have some examples which you're running, the easiest thing is to do what we showed in the third demo. So you just create new test cases and test those examples there. So you identify the important signals and you record them. So that's the first thing you can do, and that's something which can be quite valuable pretty soon, because with the next Dymola version we will get a new MSL release, and then you can test your recordings if you use the new MSL. So I think that's the easiest thing. And after that, whenever you make changes somewhere, I recommend to create a test model and test your changes in this with those test models.
Okay, and what about the work? Isn't it too much work to implement dozens of test models? And when we will benefit from that?
It is work, definitely, but I think you can make a lot of tests in a few hours. So if you keep working on it, you will be quite quick, and you will benefit from it for by every change which is made. So often you will benefit from it on the next day, because there could be changes someone else in the team was doing to your library, or there could be changes to a library you were using. So whenever there is a change, you will benefit from the tests you created. So usually it pays off.
Okay, and I have one question about the pricing, and what is the price of the library, and can I use it in other simulators like Open Modelica?
The library is free for Dymola users, so you can just use it with the default Dymola license. All you have to do is load it from the libraries menu. But it's only for Dymola users. We don't provide this library for other tools. It's exclusive for Dymola.
Okay, and there is another question here. For which models should you build test, and how do you identify the important signals?
That's something the developer has to decide. So the best case would be to build a test for every model you have. So that would be something you do during development. You make a new model, you create also a test for it. And identification of the important signals, that's not something someone else can tell you. That's someone the developer has to decide, because he knows the model best and he has to define what he wants to test.
Okay, and the very last question. Which are the most regularly used blocks for checking signals?
I think the ones we shown before, so definitely the recorders, because they allow you to easily record your existing signals you have and make sure that you still get the same results. And the continuous real check blocks. So typically you will compare the real signals, and most often you will use the recorders. But I recommend to not only rely on the recorders and to think about the signals you expect by your own, like we did with the first test model. Not just record what you have.
Okay, so I think we are okay with the questions already, and thanks Marco for your time being here with us. And for
You're
everyone who
welcome.
were with us, also many thanks for your patience, because the session was quite long, but it's a masterclass. You need to learn something, and I believe that you did. And in case you have questions, you can ask Marco or other members of Dymola team in MBSC Cyber Systems community. The link is on your screens. Marco showed also the QR code for connection. And I wish everyone to have a good day, and we will meet in other master classes. Thank
Yep.
you so
Thank you,
much,
everyone.
and bye, everyone.
Bye.